Hi, it's Dr. Harris, ready to start Chapter 3 for Math 111, and we're going to be talking some today about probability. You often hear probability attached to statistics in the phrase probability and statistics, but probability is going to we're not going to pay a lot of attention to probability in this course, but there are a few important topics that are probability related, and we need to have some foundational understanding of what probability measures, when we make a probabilistic statement, what do we mean, and things like that. So we've got a couple of slideshows on probability, and we will get started. So our first concept that we want to talk about here is that of random process. And you can see the definition I've got here for random process. It's an experiment such that you can't know exactly how it's going to turn out in advance. But if you performed it over and over and over and over again, there would be some sort of pattern of outcomes that you would be able to see. I have a few examples of random processes on the next slide. Here are 4 random processes. If you flip a coin, you don't know before you flip it whether it's going to come up heads or tails. But you know that if the coin is fair, that in the long run, if you flipped it thousands of times, pretty close to half of the results would be heads and half would be tails. Another example, an extended example on coin flipping, suppose you flipped either one coin 3 times successively, or you flipped 3 different coins and recorded for those 3 flips the number of heads that turned up. It turns out that you don't know in advance how many heads you are going to get, but you do know that you can see, if you perform this process thousands of times, that 0 will occur a certain fraction of the times, 1 will occur a certain fraction of the times, 2 and 3 as well. There'll be a pattern to the outcomes. So you could also roll a pair of dice and record the sum. Again, you don't know what the answer, when you're playing a board game, you don't know what the result of your roll is going to be, but there is a predictable pattern for the set of outcomes that you have. And lastly, a random process might be you pick a person at random from our classroom and you measure their height. Heights have a distribution. You know that in the long term, if you pick over and over and over again, that you'll see a distribution of heights arise, but you don't know what the individual height you're going to get is from a single person that's selected. So hopefully random process makes some degree of sense. We're going to now define a couple of terms related to random processes. First of all is sample space. And sample space is just going to be the set of all possible outcomes to a random process. So if we flip a single coin, we can either get heads or tails. If we flip 3 coins in a row, we're going to get either 0, 1, 2, or 3 heads coming up. If we roll a pair of dice, we know that we're going to get and add the numbers on top together. We know we're going to get a number between 2 and 12. And our heights, well, we may or may not know what the exact height of the shortest person in the class is and what the tallest person is, but let's say that it's possible we could get a number between 54 and 80. 54 would be a person who's 4 feet 6 inches tall. 80 inches is 6 feet 10. That's going to cover 6 feet 8. And that's going to cover most of the people that we might encounter in a class. Just to point out that for scenarios 2 and 3, the 3 coin flips and the pair of dice, we're going to be looking at describing those sample spaces a little bit differently in a couple of minutes. So another important idea related to random processes is the notion of event. And an event is going to be a subset, a part of the sample space. Another way to put that is it's a collection of possible outcomes. It could be a single outcome or it could be a collection of outcomes. So in the single coin flip scenario, we could say one possible event is the coin turns up heads. In scenario 2, where we flip a coin 3 times in a row or 3 different coins altogether, here are 2 possible events. We could say, oh, I got exactly 2 heads in those 3 flips of the coin. Or I could say no more than one head was flipped. So those are examples of the types of things that could be described as an outcome or a collection of outcomes from running this random process. For scenario 3, rolling a pair of dice, here are a couple of possible events. One would be we rolled a 4. If we looked at the two numbers on the tops of the dice, they added to 4. Another possible event would be, well, we roll a 6 or something lower than that. And then finally, one possible event from picking a person at random and measuring their height, we could say, well, the person selected was at least 70 inches tall. So that's a possible outcome from that, running that process. So we've got random processes, we've got the sample space, the set of all possible outcomes, and we've got events, which are collections of outcomes from the sample space. So we can come back to these 6 events that we defined earlier, just in the previous slide, and list the outcomes that are contained in them. So if the coin comes up heads, then we could describe that with a letter H. And I've got the outcomes listed here inside braces. If I get exactly 2 heads and 3 flips of a coin, I could write that as the number 2. If I get 1 or fewer heads and 3 flips of a coin, I can write that by listing 0 or 1 that's when we get 1 or fewer. If I roll exactly a 4 from a pair of dice, then I would say that the event could be described as a 4. If I roll a 6 or less in rolling a pair of dice, then I could say I got either a 2 or a 3 or a 4 or a 5 or a 6. Those are the possible outcomes that arose. And if I round heights to the nearest inch, I could write the outcome that the person is 70 inches or taller as 70 through 80, listing those integers if we're rounding. If not, I could use interval notation and just say it's all the numbers between 70 and 80. And just as I said, we're going to come back and think about scenarios 2 and 3 in another way shortly. We're also going to be thinking about events B, C, D, and E in a slightly different way very soon. And here that we are. So one of the things that's happening is when we roll a pair of dice, we could think about that as rolling 2 dice or rolling 1 die twice. Or if we flip a coin 3 times or flip 3 coins, we're really thinking about running a random process repeatedly. And so one of the things that's going to be useful to us when we're talking about probabilities very shortly is that it's often useful to list the individual outcomes in a different way. So rather than saying I flipped 3 heads, I flipped a coin 3 times and I got 2 heads, I could actually list the order of the results. And in that case, it could have been heads, heads, tails, heads, tails, heads, or tails, heads, heads. So I'm thinking about there's an order to, I'm thinking about the first flip, the second flip, the third flip. And when I'm rolling a pair of dice, I'm thinking about one of them is the first die and the other one is the second die. And so you can see here I've listed the 8 outcomes for flipping a coin or flipping a coin 3 times or flipping 3 coins by listing the outcomes in order. So 3 heads is now HHH. The next 3 items in the list are the 3 ways I could get 2 heads. The next 3 after that are the way I could get 1 head. And then finally, tails, tails, tails is the way I would describe getting 0 heads. So it's going to be useful to us to think about not just recording the number of heads, but thinking about the sequence of results from those 3 flips. Likewise with the dice, we either can call one of them the first die and the other one the second die. It might be easier to keep track of it if you think about them being different colors. Say one of them is red and the other is green. Then we can list the result of a pair of dice, a roll of a pair of dice by listing the results in order. Say the red die first, the green die second. And I've listed some possible outcomes here. 1-1 would be, both of them came up 1. 3-4 would be the red die was 3, the green die was 4. 2-5, the red die was 2, the green die was 5, etc. And we'll come back and talk about why there are 36 different possible combinations in just a minute or two. But I just want to point out that coming up with these ways of thinking about not sums of of results, but actually listing out the results in some sort of order, the individual results in some sort of order when we've got a repeated process, that's going to be very useful to us. Okay, so let's recast these our scenarios and our events in light of this new way of considering these outcomes. So the event B, where I flipped exactly 2 heads and 3 flips of a coin, I would now list that instead of just the number 2 as HHT, HTH, THH. And the event C, which was getting 0 or 1 head, I could list as those 4 outcomes, TTT, TTH, THT, HTT. The event D, rolling a 4 from a pair of dice, can now be listed as the 3 different outcomes, the 3 different ways I can actually get a 4. I could have a red 1, a green 3, a red 2, a green 2, or a red 3 and a green 1. And think about the event E, rolling a 6 or less. How would you list all the possible outcomes there? I'm hoping that you can do this, but we'll take time to go over this in class as well. So now that we've got this alternate way of thinking about outcomes of a random process, we can now talk about probability in some particular cases. So when we talk about an event and assigning a probability to it, we're talking about assigning a number between 0 and 1, and that probability tells us how likely that event is to occur. The higher the number, the more likely the event is to occur. If I say that I have a probability of an event that never happens, we would assign that a probability of 0. And if I've got an event that always happens, then that's going to be assigned probability 1. So probabilities are numbers between 0 and 1 attached to events. So the problems that we're going to be looking at here at first, we've got a relatively small number of possible outcomes, and we're going to be assuming that each outcome is equally likely to occur. That's what happens when we divide the outcomes up as we did here. Back here, we were writing things in such a way that these outcomes were equally likely to occur. The 8 possible outcomes right here, all equally likely. The 36 ordered pairs for dice outcomes, equally likely. So if we can tell that we've thought about our sample space and describing the outcomes so that they are all equally likely, then the probability of an event occurring is going to be the number of ways we can get what we want divided by the total number of possible outcomes. So a capital P next to an event is going to stand for the probability of that event occurring. So P of an event is the number of ways the event can occur divided by the total number of outcomes in our sample space. Looking at a few examples, we mentioned already that there are 4 ways to get either 0 or 1 head in 3 flips of a coin. And these are the 4, TTT, HTT, THT, TTH. We also mentioned that there are 8 possible ways of getting outcomes from 3 flips of a coin. So 4 ways to get what we want, 8 possible ways overall. So the probability of getting at most 1 head, that is getting 0 or 1 head in 3 flips of a coin, is going to be 4 divided by 8, which we could reduce to 1/2. If we want to know the probability of rolling an 8 from a pair of dice, well, we need to list out all the ways that we can get an 8 using these equally likely outcomes. And so if we meditated on it a little while, we would see that there are 5 ways to do it. I get a 2 and a 6, a 3 and a 5, a 4 and a 4, a 5 and a 3, or a 6 and a 2. So as I mentioned, there are 36 different possible combinations. And the one way to see that is that if I think about the first number being the result of the red die, then for each of those 6 outcomes on the red die, I've got 6 outcomes on the green die to pair with it. So 6 times 6 gives me 36 combinations. So 5 ways to get what I want, rolling an 8, 36 different possible outcomes for rolling the pair of dice. And so the probability of rolling an 8 is going to be 5 divided by 36. Similarly, if I wanted to know what's the probability of rolling a 9, I would see that there are 4 ways of rolling a 9, and I've listed them here. And so the probability of rolling a 9 is going to be 4 out of 36, or 1/9, if you want to reduce the fraction. Next, I want to define a few terms so that we can describe 3 probability rules. And so the first new term we want to get is define what it means for events to be mutually exclusive. And 2 events are mutually exclusive if they cannot happen at the same time. And that means that they would share no outcomes in common. So here I've listed 3 examples for us to consider. Getting exactly 1 head in flipping 3 coins, or getting exactly 2 heads in flipping 3 coins are mutually exclusive. It's impossible to get both exactly 1 and exactly 2 heads when I flip a coin 3 times in a row, or flip 3 coins. Rolling an 8 and rolling a 9 are also mutually exclusive events, because when I roll a pair of dice, it can't be both an 8 and a 9 simultaneously. On the other hand, if my events were rolling an 8 and rolling an even number, those events are not mutually exclusive, because, as we know that 8 is an even number. So if I've rolled an 8, I've definitely rolled an even number as well. So it's possible for both of those things to happen at the same time. Doesn't mean they have to happen, but, well, it does mean if I roll an 8, I've rolled an even number. But if I rolled an even number, I don't have to roll an 8. But because they share some outcomes in common, they're not mutually exclusive. So let's talk about a probability rule when we can tell that we've got mutually exclusive events. If I've got 2 events I'll call A and B, we're going to say that A or B means that either one or both of A and B have occurred. So either A has occurred, B has occurred, or both A and B have occurred. So if in the case where A and B are mutually exclusive events, then the probability that one of them occurs is going to be the sum of the probabilities that they occur, because there's no overlap. We can just take what's the probability of A, what's the probability of B, and just add those 2 numbers together, because they don't share any outcomes in common. So a couple of sort of quick examples. The probability of flipping exactly 1 head or flipping exactly 2 heads in 3 flips of a coin is going to be the probability of getting exactly 1 head plus the probability of getting exactly 2 heads. There are 3 ways of getting exactly 1 head: HTT, THT, TTH. There are exactly 3 ways of getting 2 heads: HHT, HTH, THH. So the probability of getting exactly 1 head is 3/8. The probability of getting exactly 2 heads is 3/8. And so because they're mutually exclusive events, the probability of getting one of those 2 things happening is 3/8 plus 3/8, which we add together to get 6/8, which we can reduce to 3/4. Similarly, if I roll an 8, I want to know the probability of rolling an 8 or a 9. We've already calculated the probability of those events individually, and because they're mutually exclusive, we add the probabilities together, in which case we would get 5/36 plus 4/36, which is 9/36, or 1/4. So the probability of getting an 8 or a 9 in a single roll of a pair of dice is 1 out of 4 chance. The mutually exclusive rule applies to more than 2 events as long as no 2 of the events can happen simultaneously. And so if I want to know what the probability of rolling a 6 or less, well, to get a 6 or less, that's the same as I either rolled a 2, or I rolled a 3, or a 4, or a 5, or a 6. No 2 of those overlap, and so we would add all 5 probabilities together. If you think about what the individual probabilities are, there's only 1 way to roll a 2, 2 ways to roll a 3, 3 to roll a 4, 4 to roll a 5, 5 to roll a 6. And so the probability is going to be 1/36 plus 2/36, etc. Gives me 15/36, which we reduce to 5/12. The next thing we want to talk about is what it means, what the complement of an event is. And so if I give you an event, its complement is going to be the set of all outcomes that are not included in the event I gave you. So if my event is rolling a 6 or lower, then the complement of it is going to be rolling a 7 or higher. If I tell you that my event is I flipped exactly 2 heads in 3 flips of a coin, then complement of that is going to be I either got 0, 1, or 3 heads. And we're going to use the notation A, or if A is my event, then A with a superscript C is going to be the way that we denote the complement of an event. And we will read that A superscript C as a complement. We have a probability rule for complements. If A is an event, then the probability of its complement occurring is going to be 1 minus the probability that A occurred. So the idea is this: either A occurs or it doesn't occur. And so A and its complement are mutually exclusive. If one of them has to occur, then the sum of their probabilities has to be 1. So that means that if I know the probability of A occurring, then I can just subtract that probability from 1 to get the probability of the complement occurring. So if I want to know what's the probability of not rolling a 6 or less, or i.e. the probability of rolling a 7 or higher, since the probability of getting a 6 or less is 5/12, the probability of not getting a 6 or less is going to be 1 minus 5/12 or 7/12. And since the probability of getting exactly 2 heads and 3 flips of a coin is 3/8, the probability of not getting exactly 2 heads and 3 flips of a coin is going to be 1 minus 3/8 or 5/8. The last definition I want to go over in this slideshow is that of independent events. 2 events are said to be independent if knowing that one of them, if I told you that one of them occurred, that would have no impact whatsoever on what the probability of the other one occurring is. So here's an example of a pair of events that are independent. I flip a coin and I roll a die. If A is the event that the coin flip would round up heads, and B is the event that the die rolled came up 6, those events are independent. If I told you that the coin flip came up heads, that wouldn't have any impact on what the roll of the die was. So A and B are independent because knowing either the outcome of the die or the result of the coin flip doesn't have any impact on what the outcome of the other one was. Another important example of independent events would be the results of 2 successive coin flips. Just because the first coin came up heads, when I pick it up, the coin has no memory, and so the probability of getting a head the second time is still 50-50. But the example at the bottom of the slide gives us an example of a pair of events that aren't independent. So suppose C is I roll a pair of dice and it comes up 9, and D is the event that one of the die I rolled is 6. I'm saying that these events are not independent. Let's see why. Okay, so a few slides ago, we saw that the probability of rolling a 9 is 4/36 or 1/9. But now let's imagine that I didn't show you the dice as I rolled them. I hid them from you. And so I rolled the dice, and then I showed you the result of the red one, and it was a 6. So now you know that one of the dice came up 6. What's the probability that I rolled a 9 now? Well, let's see. My space has been limited now. Because the red die came up 6, I know that there are only 6 possible outcomes. 6/1, 6/2, 6/3, 6/4, 6/5, and 6/6. Because I've told you that one of the dice came up 6. Well, since I'm limited now to that set of outcomes, exactly one of them, the 6/3, has a sum of 9. So once I tell you that one of the die came up 6, the probability of getting a 9 has now changed to 1/6. So that means that the 2 events are not independent, because before I told you anything, the probability of getting a 9 was 1/9. But once I showed you that one of the dice was a 6, then the probability changed to 1/6. So these events are not independent. Knowing the outcome of one, knowing that one of them had occurred, impacted the probability of the other one occurring. But if I can tell that I've got independent events, then there's a nice probability rule. So A and B is going to stand for the event that both A and B occur. So if A and B are independent, then the probability of both of them occurring is the product of the individual probabilities. And as I note here, that also extends to 3 or more events that are all independent of each other. So a couple of quick examples. If I flip a coin and I want to know what's the probability of flipping a coin and having it come up heads and rolling a die and having it come up 6, the probability of both of those things occurring will be the probability of A occurring times the probability of B occurring. The probability of getting a head is 1/2. The probability of getting a 6 is 1/6. We multiply those together, so there's a 1 out of 12 chance that we get both a head and a 6. Suppose I flipped 3 coins in a row, and A is the event I got a head the first time, B is the event I got a head the second time, C is the event I got a head the third time. What's the probability that all 3 of those things occurred? Well, the probability of A and B and C occurring is going to be the product of the 3 probabilities, 1/2 times 1/2 times 1/2, which is 1/8. And just note that we computed that probability differently in an earlier slide. The probability of getting exactly 3 heads would be 1 out of 8 because heads, heads, heads comprised 1 of the 8 possible outcomes. We'll be having more on probability in our next slideshow.